So in RF front-end design, after the LNA part, the next important building block is the frequency synthesizer. And the frequency synthesizer, the main block is the VCO, the voltage control oscillators. So I am going to design of a voltage control oscillators using the same 2.4 gig frequency for Zigbee or other applications. So let's go very quickly, because then it will be also be shown in online simulations to design it. First of all, what kind of oscillators you will be using for your frequency synthesizers? There is lot of confusions comes among the students. Should I go for ring oscillators? Should I go for the LC-VCO or other kind of oscillators, which is much easier to implement, takes less area and power? But I find that look at your phase noise requirements. When you have more number of channels to handle in a small bandwidth, then you cannot afford to have a phase noise worse than minus 110 dBc at 1 gigahertz, at 1 megahertz offset at 2.4 gig. So you require actually a better phase noise performance, where this kind of ring oscillators, which are very easy to implement, will not be used. So only options you have to have a better phase noise is LC oscillators. So LC cross-coupled oscillators is the options you have, where the phase noise performance is very stringent, because you have to handle a huge number of channels in a small band. So I'd say that what's phase noise performance in this kind of ring oscillators, where in case of this LC-VCO you will have better phase noise performance. Another one is that suppose you want to design a RF front end for 2.4 gigahertz, then it is better you can make your VCO 2 times of that frequency. Suppose it is 950 megahertz is your GSM phone, so your requirement is actually 1.9 gigahertz kind of VCO. Why? I will explain later on. So twice the RF in frequency is the requirement for your VCO. Then you can handle the further processing of your signals in a better way, because you can both in phase and quad phase components much easier with a divider, and you can make use of that for accurate prediction of the phase and the frequency. So what I say that essentially LC-VCO is not come in alone. So LC-VCO, say for example you are doing it for 1 gigahertz, 1.8 gigahertz, then you have a frequency divider. It is basically a flip-flop, and then you have both the in phase and the quad phase components, and that divider is divided by 2. That will give you a 900 megahertz. That 900 megahertz is your GSM RF in. And also you have the injection lock-in divider, because sometime what kind of divider you will be using, that will come in later on. You can have current injections to that for better performance and so on. So let me go straight to the VCO design. So the typical topology of any kind of VCO means LC tank is a cross-coupled VCO. What is that? You have both PMOS and NMOS pair, and which is being connected with a tank circuit, which is a parallel combinations of a variable capacitance and an inductor. And this variable capacitance is basically MOS varactor. And this MOS varactor, if you look at the transformation of any MOS varactor, you have to think in a minute manner that what you want. You want actually variable of this capacitance across the frequency or voltage. So if you look at the capacitance like C aux by C, and this is a V in, so you know that your capacitance is decreasing up to VTH, and then it is going up. So you can use this part as a variable capacitor on. So I am talking about this one. This is the variable. This is the variable cap, or this is the varactor. Now this variable cap will be assisted by bunch of fixed capacitors. I will come later on. For example, in Zigbee applications, where your frequency range is from 2.4 to 2.78 gigahertz. Now if there is 78 channels, then you have say 78 channels, so you have the channel spacing delta f will be 1 megahertz. Okay. And if you look at the frequency tuning, that is your delta f will be 78 megahertz. But look at here, for an 1.8 volt systems like is 180 nanometer, your range of voltage VTH is 0.5 volt or 0.6 volt, right. So it is here the 0. So you can vary it from say 0.2 to 0.4 volt to have the operational linearity of this is the operational region of your voltage. So what I say that your delta V equal to 0.4 minus 0.2 equal to 0.2 volt. So then what is KVCO? That is the frequency tuning range of this is KVCO equal to delta F by delta V, which is 78 megahertz divided by 0.2, and that is equal to how much it's coming is 390 megahertz per volt. So this is known as the gain of the VCO, and that is very, very huge. KVCO gain is what? You think you're physically, what does it mean? That if there is a small change in voltage, that reflects into the change in frequency. So if there is a small variation in your biasing voltage, or if there is small variation in say temperatures, then that small delta V will account for that into 380. So that much of frequency variations you will be having. So much KVCO, high value of KVCO is not a desirable design. Make it within say 100, 70 megahertz, 40 megahertz, 20 megahertz per volt. That is the first thing. How do you do that? Now to do that, you have only options is to have this earlier design called band select filters. So what is this? You have your cross-coupled systems, then you can actually have several such. So what you can do that, in spite of this single MOS varactor, you can have this multiple bank of capacitors, and that capacitors will be connected with a switch. So in that case, what will happen? You have in your expressions, you have this omega equal to 1 by root over of L, then C variable plus C fixed. So these fixed capacitance are provided by those capacitors. So you can select the band. For example, I make each of this, I will show you digitally. You can control by a 4-bit or 6-bit binary weighted digital bits to turn on those MOS switches, so that the capacitors connected to the ground and add parallel to this capacitance and can shift the frequency from one band to another band. Then when it goes to a particular band, then you have say 1 megahertz. So within 1 to 5 megahertz you can control. For example, 16 how many bits? 2 to the power 4, 16 minus 1, 15. So you can have 15 such bands. Okay, so 78 megahertz or 16 for making easy. So I am making 80 divided by 16. So 5 megahertz. So I can use those switches from say 2.4 to then 2.47, 45, then 2.5, 2.55 like that by those coarse tuning. Okay, by those capacitances I can actually select the band from starting from 2.4, then 2.45 and so on, 2.405, then 2.41, so 5 megahertz spacing. And then within this 2.401 and 2.4, I can actually tune it with that fine tuning using the varactors. Clear? So I have two tuning characteristics. One is by band select switch these capacitors, and also by fine tuning by the variable capacitors. So if now the delta V is 0.2 and your frequency tuning range is 5 megahertz, then 5 megahertz divided by 0.2 is becoming 10 megahertz per volt. So, it's from 390 megahertz per volt, I am going to 5 or 10 megahertz per volt using those band select capacitors. So, in that case your KVCO is much less, so your noise contribution will be much less. That is why you are using the capacitor bank, binary weighted capacitor bank, to implement the VCO. Now, coming to this, if you come into the next one, that you can have both these. Again, the constraint is that the VCO, it is a PMOS cross coupled and NMOS cross coupled. I will let you know why you are using both complementary architecture, and this is the tail current with a mirror source, and this is a variable cap. It can also be done by simple and NMOS or you call pseudo CMOS oscillators. For when you have this 1 volt, supply here, then biasing these two transistors may be difficult. So, you can go to this pseudo CMOS or simple NMOS characteristics. So, you understand this cross coupled stuff can be done using the NMOS or CMOS cross coupled pair facing an impedance which is a tank circuits. So, this way you can handle it 1 volt, either 1 volt between the two cross coded one, or the 1 volt just swing one such cross coupled pair. Now, look at here, when you have this complementary pair, in this case when you have this only n type cross coupled pair, then the impedance as seen by this tank circuit consisting of the L and the variable capacitors is -2 by Gm. Okay. So, what is the basic principle of operation of any oscillators? That if you look from the active side, you will have a positive impedance, and if you look from the other side, that is from the tank side, if you see that active side, you will get a negative impedance. So, positive impedance dissipates energy, and negative energy is actually creates the energy. So, oscillation goes on, and that is why when the Barkhausen criteria is satisfied, you will have the sustained oscillation within the systems. So, basically the cross coupled pair is here is to have a negative impedance with respect to the tank circuits. That is the reason why you are using a cross coupled pair. And secondly, you can utilize only N coupled pair, that is 2 N type transistors coupled, cross coupled. In that case, your impedance in is 2 by Gm. Now, if you look at here, the Barkhausen criteria as I mentioned, then Gm into Rp, Rp is the impedance or the resistance as seen from the active circuit, that is Gm into Rp. Okay, I will give you that must be greater than 1, which is the condition for sustainable oscillations. Now, if in this case, go to the cross coupled one, in this case, you are getting 2 by Gm as well as 2 by Gm. So, 4 by Gm, but it is only 2 by Gm. So, in this kind cross coupled one, you are having 4 times Gm. So, but you require whatever condition you require for Gm into Rp greater than 1, whatever Gm you require for a single coupled one will be much less, at least half of the Gm is less in case of cross coupled one. Then what is Gm? Gm is equal to square root of twice mu n Cux Wi L IDSS. So, in this case you will have less current consumptions. So, the same Barkhausen criteria, that is the oscillatory condition, whatever Gm need to be achieved can be done much lower current, at much lower current in a cross coupled pair. Whereas, in case of a single, that is N type or P type, whatever you use for a single cross coupled pair, you need more current. So, for power consumptions you can go for the cross coupled one, but the cross couple having a problem of this voltage headroom which needs to be solved out. So, what I said that this complementary structure chosen provides more energy to the tank, so that you are requiring less current to satisfy your oscillation conditions. Now, come to this. you are using this band select capacitors to reduce the KVCO, and and then you are using this another tricks I like to mention over here, that the cross couple pair having connected with a capacitor, which is a deviation from the conventional design, because it has been found that suppose there is a input swing from low to high and then going down, then you remember this voltage here will go up and the voltage here will go down, right. This is a complementary behavior. So, if it is a differential stage. So, here if the voltage going up, here the voltage will go down in the same phase, right. So, now look at here, the conditions for its saturation. What is the reason we have to use a capacitor for that, that I am explaining now. So, your condition is that the VDS should be greater than VGS minus VTH. That is the condition for saturation, transistor in saturations. But suppose the voltage swing up, if it swing up, then the difference between them is going down, and on the other hand, if the voltage goes up, then your VGS is going up. So, that way actually the condition of this VGS VDS is greater than VGS minus VTH is not satisfied in one condition of the input signal or the signal swing when it is going in upward directions. Therefore, these transistors might go into the linear region. If it goes into the linear region, then your all oscillation will stop. Therefore, to ensure the transistor works in the saturation region, you can use a capacitor cross couple, which will slow down the process of this difference, and you will find it that the conditions is always achievable to have these transistors working in saturation regions. So, this is the one of the deviations I said, but you should have if you get one advantage, then you should ready to pay something. So, to pay something is that you know that now this gate of this transistor are actually the DC is blocked by these capacitors. So, although in the small signal it is fine, but how to feed that transistors with the DC bias? Then you can use this technique, which is called the common mode technique. I am giving you this, the idea. So, you can make this kind of biasing technique to bias those one. So, what is this, the common mode one? You have one resistance, okay. You want the voltage should be same in both the sides. So, you have two resistance, same resistance. From the between the middle of this resistance, you are taking the node and putting in a differential pair and remember that, and then output of that is goes to the two resistance, and one is feeding this gate and another feeding this gate. And so, your you have to remember that to have a symmetric swing, the voltage should be the same in both the sides. So, if one of these voltage is going up by any chance, then you should have a reason to reduce it down. So, look at here. Suppose the voltage here is somehow it is going here is more because of the asymmetric conditions. Then if this more, then the voltage output will be high. If this voltage output will be high, then it will be high. Then if it is high, then this transistor will go to this is a P type. If the positive voltage goes up, then actually the current will go down and the voltage here will be going up. So, this is way how the voltage here is actually going up and this will going down. So, this way how a negative feedback and a common mode feedback with a negative approach can be balanced, and your and you can have an equal voltage combinations in both the cases. So, that is the how you should be able to bias this cross couple pair using this technique. So, you can use one cross couple pair with those capacitors, and also you can use one this common mode feedback to ensure stable and symmetric operations of this VCO. Next one is important, that if you look at the scenario here, this is at 1 volt, the PMOS, and this is the n type cross coupled pair and the 1 volt supply. If it is 1 volt supply, then there is a possibility that transistors would go to linear region, even goes to cutoff region, because of the it does not have enough voltage headroom. To avoid it, you can use actually low threshold voltage transistors, cross coupled pair, where the typical voltage is 50 millivolt. So remember that PMOS low voltage, low VTH is not available in the market. In the foundry will not support the low voltage, but here native MOS is only available in the N type transistors and typically say 80 millivolt. So by introducing the native MOS, actually you can circumvent this voltage headroom problem. And you remember, this is the mirror, current mirror as the tail current source. So this is isolated. I say that the native MOS should not see the ground or should not see the VDD. So it is now isolated by these transistors, these are normal transistors, and those pair of transistors, which is also normal VTH. So that is the scheme we have utilized to develop this VCO using a cross coupled pair, and then I am going into the actual design. So I summarize, the voltage headroom solutions has been solved by NMOS pair replaced by the native MOS, and PMOS pair is capacitively cross coupled to avoid this unwanted transistor operations, to ensure that it operates in saturation region. Then common mode feedback is required to keep the DC level fixed, and the supply sensitivity of the frequency decreases as the DC bias across varactor does not change with supply. So like here KVCO, there is another term KVDD. KVDD means the change of frequency with respect to the change in the biasing voltage, that is delta F delta VDD. So those common mode technique which have been utilized here can also help you to make this design more robust in terms of the fluctuation of the voltage variation in the bias. These are all the deviations from the textbook design, which comes from our design experience. Then bank of switch capacitor is used. So KBCO is 50 megahertz now, and which improve the linearity of the frequency change, and it consumes the core VCO that consumes say 2.5 milliwatts of power. Coming to the next, I said that when you suppose I am using it for 900 megahertz for GSM phone, then my local oscillator frequency should be able to produce 1.8 gigahertz. Now this 1.8 gigahertz is fed to this divider, and this is a latch. So you can actually both the input and the quad phase output will come, the differential output will come from that. So that is simple circuit, a frequency divider by D flip-flop using 2 latches, and then considering this the condition of self oscillations, that is GM into R. You remember, while you are using this divider circuit, the self oscillation frequency of the divider should be much high compared to the operating frequency. So for example, if the input frequency is 1.8 gigahertz, then self oscillation frequency of your divider should be at least 10 gigahertz. Otherwise your divider will oscillate into that modes of frequency, and it will not work finally, because actually it is a frequency divider block. I have 1.8 gigahertz, I want 900 megahertz in both in phase and the quad phase components. And then you this particular frequency divider block is supposed to consume 1 milliwatt of power. Now coming to the simulation part. First of all, you have to look at the transient simulations. Now once you start the transient simulations, you know that first you know that how the simulation builds up. So initially you will find some small undulations, and then finally it starts. So the point when you have the equal amplitude and from the 0, it is called the transient time, that means the settling time. So settling time should be much less, as much as possible. So that is an important criteria to build up an oscillations. And then you can have this phase noise performance and the tunability. This is the most important curve which you have to understand carefully. So what is that I want? I said that how many such frequency tuning curve. This is the control voltage VC, and this is the frequency, right? So this is from 0, 0, 0. That is, all your capacitors are actually off. So all your bank or capacitor banks are isolated. So your VCO is working with 1 by twice pi root over of L into C. C is the varactor capacitance. So capacitance is much less. So you will have the highest frequency. Okay. Now if you vary the voltage of this variable cap with respect to the voltage, you are finding these variations of this voltage. Now if you go down, that means if you add say 0, 0, 0, 1, that means one of the capacitors get attached to your both the sides to the one. So your frequency will go down. So you are seeing its frequency is going down. Then you go to 0, 0, 1, 0, like that binary weightage, those switches being on, and your voltage to frequency, the frequency tuning curve is going to lower frequency. Okay. So this is the KVCO. Slope of this is equal to the KVCO of this. So this is, if you take the slope of that, and so you understand it's not a steep rise. So that is I require. I need a very smooth ride over the frequency voltage tuning. I don't want any sharp rise that will introduce some kind of huge noise in the system and instability. So that's why how by using this capacitor and the bank with the varactors, you make use of this for lower KVCO and stable oscillations. Then typically you say that this is a very old work, 2007. So look at here, the phase noise performance at 1 megahertz offset is at 3 megahertz offset is minus 133 dBc. So when I will go into the frequency synthesizer design, I will go into more details of how to tackle the phase noise performance. And KVDD is 6 megahertz per volt, and power consumption is, I say, 3.5 milliwatt. And then you know that you can, in the literature or any text or whatever in a patent, you will find various process, and these are the various parameters. But how would you benchmark your VCO from your design to others? Then it is better if you define a figure of merit, which is the signal strength at the, or the swing at a single side band. Delta F is the frequency tuning range, F0 is the center frequency, PVCO is the power consumptions, and that will give you some kind of a figure of merit, and that would be your estimated benchmark with respect to others' work. So that is a better things that you define your figure of merit, and then you just compare with others' work, because somebody has got, what I am saying that, suppose somebody has got a better phase noise performance, but look at their power consumptions. If you can burn more power, you can always achieve better phase noise, but it doesn't have any meaning at all, because I like to have the less power consumptions, okay, but with some comparable phase noise performance. So that's why I am saying that you have to make some kind of comparison bench to normalize all the performance into one scale. So this is some kind of this approach. So you define a figure of merit to find out the relative performance of those others' work and compare with your work. I am not up to that simulation. All the measured data I will show you, just wait. So after the design and simulations, then you remember it's pretty old design, so large area 180 nanometer process. So this is the tank circuit, the inductor. You can see that it is almost 3.5 kind of a turn, okay, and then you have those varactor and this cross couple pair and this 1.2 millimeter into 1.2 millimeter. Nowadays people work with complete transceiver is 1.2 millimeter into 1.2 millimeter. Anyway, for the class, today's class, you can, it is okay, this is for, and you can do, this is the pad, how this is connected to this external pins and so on. So you can find this is a simple LC VCO and with say 900 megahertz kind of oscillations. That is 1.8 gigahertz oscillations, and the divider will be there so that you can get at ultimately 900 megahertz. And this is a bias generation circuit. Somebody talked about that. This is a bias generation circuit. So this is the inbuilt bias generators inside the chip. This is 180 nanometer national semiconductor process, 1 volt. Mind it, the challenge of the design is this is a 1.8 volt supply, but we are designing it for 1 volt only. So restricted our voltage scale to 1 volt. So after the design, then you have the pins. So this is the KGP, this is KGP LC VCO, and then you have to make a board. So remember, if you look carefully about the board design, the board should have, it is 900 megahertz or 2.4 whatever, it should have an impedance matching, and this is a M connector. So all this connection, this is the PCB, where that should be matched with special RF PCB softwares are available, where you have a tapered kind of junctions. So you have to taper this so that impedance is matched to that. It is not standard PCB where the interconnects are straight lines, but you need a tapered one so the impedance gets transformed. So these are the few things you have to understand, and these are all these, you have used simply DIP package, which is not good. You have to use QFN kind of packaging for high frequency and so on. So this is the design, and the PCB and the chip is placed on that, and then we are measuring that one. And before that, one of the most important part is you should have a proper pad design, means your pad and pins should be modeled accurately. What does it mean? What informations you should have when you talk about this pad and pin parasitics? So if you look at here, that should be available from your vendor. So look at here, if it from this is the oscillator, right? And the oscillator, you need a buffer. This is an important step. Suppose you have an oscillators and you are just making a measurement of that, your oscillation will simply go to ground because of this capacitance. So you have to isolate, or the probe capacitance will actually shift your frequency from 900 megahertz to say other frequency, say 500 megahertz. You might say my oscillator is not working, but actually it is working, but unnecessarily one capacitance is added from your probe. So how to isolate the external capacitance with respect to the internal one is to use some kind of a buffer. So that buffer is simply a source follower. Okay? So remember, in your circuit when you do the layout, don't forget to make those kind of buffer. Whenever there is an external pin, you should have a buffer to avoid this impedance mismatch or the parasitic capacitance. And then you have the pad. Pad means the pad which goes to the pin side. I gave you this rectangular pads. That pad would have those electrostatic, means that the reverse diodes paired, so that you can have the electrostatic discharge can be avoided to that, which is 100 femtofarad capacitance. These are all on chip ESD protection block. So that will be available by say TSMC, what process you are doing. They will give you this information, that what kind of electrostatic discharge you have to use for this. So that will give you, they will provide you this idea, and then this model, and then this is the bond wear. So this bond wear needs to be modeled. So whatever model we have used in this is modeled in that way. So it is 3 milliohm resistance, then 700 picohenry is the inductance, and 140 femtofarad is the capacitance. So this is the bond wear parasitic value, and that goes to pin, and that pin goes to then to 50 ohm impedance. That means the PCB line of 50 ohm. So clear now? So from starting from the chip inside, how you have to route all your design up to the PCB. So that involves first is that the buffer to isolate the effect of the loading, and then you have to use those bond wires. So proper model should be ensured, then pin, and finally goes to the PCB, and then PCB layout should be made so that the gradual impedance transformation occurs like that. Okay? So after that, next is the first measurement you have to carry out is how it tunes. This is the measured data. The measured data shows that if you look at the voltage, this is the control voltage. So how much I can change? From 0 to 0.6 volt. Okay. So if you change that, then the frequency is, I say it is before the divider. So this is the actual oscillation frequency, 1.8840, 1.8901, so on. So this is the frequency of oscillation. So one point, that when you make the silicon tape out data, then suppose you are designing for say 1.8 gigahertz. Frequency that will always obtain is less than that. Always. This is the Murphy law. Suppose you are designing 1.8 gigahertz, whoever be the designer will get little less than that. Why? Because of the parasitic capacitors that is coming in parallel to that C fix, and that cannot be modeled. That is the inaccuracy of your capacitance model. Fortunately, that will add to that. So what will happen if C fixed is added with a delta C, that will reduce the frequency a bit. So don't get frustrated. That means your circuit is operating. So that's why you are having those kind of controls. 4-bit control is there. So it is called free running frequency. So free running frequency, if you design in for 1.8 gigahertz, if it is little less than that, don't get worried, because you have a fine tuning. So you can always tune it to the free running frequency. So that is one approach I should tell. And then look at here, this is my measured data and this is the simulation data. So I have got a huge difference of the simulation data and this measured data, and I kept this for you only because how I have learned the design from that. So this is the learning stage, this is the first VCO. And later on I explained that why actually my frequency tuning shift so much difference in it. So what lesson I should learn from that? So I will explain it one by one. And then you come to this, just remember this point, why these variations. Then I said, what is this? That I have a free running frequency and then I have a bank of capacitors. Now by a 4-bit control, I will actually, my band select switch will make the capacitance added to the parasitic cap or the variable cap, and then I will give you the corresponding thing. So you can find out that when it is 001, so it is 1.86, and then you are getting all those bands filled, all those bands. So 1.86 to 1.84, okay, so 20 megahertz roughly, and then he is going to 1.82, then 1.8 and 1.79. So this is the band selection. That is simulation data. And if you look at here, this is the oscillation, okay, and this is a pretty interesting results at that time. But later on, you know that only this one is called the sparks. So those sparks, those unwanted jerk in this spectrum is a very interesting thing. Later on, one PhD thesis came out of that, how to reduce the spark, and that is a very interesting work carried out by one of my PhD students to that. I will explain when I will design the frequency synthesizers. But remember, more or less, this is the spectrum of a very standard VCO at 900 megahertz or 1.8 gigahertz before the divider. Now, why this question comes that I have a difference from my oscillation frequency, and because we have used the digital CMOS process, and in the digital CMOS process, the AP layer is doped. Okay, if AP layer is doped, then you have eddy current loss will be high. So your quality factor that we have taken to be at 3 and 4, that is even much worse. So you have to use, if you want to have a very stringent about the power consumption and the phase noise performance of that, then you have to be careful about how is your substrate looks like. So your substrate should be heavily, I would say that it should be insulating substrate. So prefer non-AP layer. So if you have a non-AP layer or undoped AP layer, non-AP means non-undoped AP layer, then it will give you much better performance. So we have made a model and later on proved this, that the phase noise performance measured was -1, there is the simulated data. He is asking that what is the data you got, -1111 dVc hertz, but I got much better result later on. But I am showing you the worst performance because of this quality factor that depends. And so you have to really careful about your substrate. The substrate affects very much on the quality, on the phase noise performance and its power consumptions. So I am quickly going to this, and then I will go to the actual design of an oscillators using 65. I am just quickly go through the design things, that if you design an 1 gigahertz oscillator, for simplicity we are not going to the complementary one, we are giving simply an NPOS 1, and assuming that I am using VDD of 3.3 volt and corresponding Kp equal to this one, and assuming Q equal to 10 and so on, then you are using 4 milliampere current is drawing through that, just to give a bird's eye view how to design these things. Then actual simulation will come. Then you have to calculate first the W/L ratios of those transistors, and then you can calculate the MB means the biasing transistors, and then you calculate what is the voltage difference VGS 3.3 minus 1 volt is 2.3 volt, and then calculate the V peak, what is the peak, this is the peak swing of the LO oscillators, which is I bias into the RP, where RP equal to RS. What is RS? RS is the series resistance of the inductor. So I bias, which is a biasing current flowing from the VDD, multiplied with the series resistance 1 plus Q square. So Q is so important, so that your peak, that is the swing of your oscillator, depends on that. And then RS you can calculate from this value. So for example, V peak, I say V peak equal to 2 volt, because there is a drop of 1.2 volt there, and 1.3 volt, and 3.3 volt is my VDD, so drop is 2.2 volt, so that will give you the value of 5 ohm. And then if you know this value of RS, then you can calculate for a given frequency the L, so that L value comes out to be 7.96 nanohenry. Then you know that what is the frequency of oscillations. If you know L and C, then if you know the frequency, you can calculate the capacitance. Then capacitance is coming to be 3.18 picofarad. And then coming to the Barkhausen criteria, that is this GM must be greater than RS C by L, and from there you calculate the transconductance of your transistors, which is a cross coupled pair, and that transconductance is equal to 2 into 10 to the power minus 3, assuming that criteria, and I say it is 10 times of that, much higher. So within 10 times of that, it becomes 20 into 10 to the power minus 3. Then using this expression, which is everybody, that is the standard equations, so I can calculate the W/L ratios. Then I have assumed that L equal to 50 micron, and from there I calculate the W. So that is the whole design steps for the LC coupled oscillators for a standard 180 nanometer CMOS process. So now he will show you the actual design online. What is the? So we have used the differential QVCO, and the output stages is one is Q, that is the frequency that is coming out. Then I give a D flip flop, and that provides me the in phase and the quad phase components. So 1.8 gigahertz is coming from my oscillator. Okay, then I am taking one of them is going to my D flip flop differential. It is a differential D flip flop, and from the D flip flop Q and Q bar. So that Q provides me the in phase and Q bar provides me the out of phase components. So that is way how we have make the in phase curve. But that's why I say that I have not tried to generate the quad phase within the oscillators, but I try to generate the phase difference in the D flip flop itself. That gives me much simpler VCO design rather than inventing something within the oscillator itself, because make sure that the oscillator should not consume more than 2.4 milliwatt of power. And 2.4 milliwatt power plus if you have a common source buffer, that will keep a budget of 1 milliwatt. So that 1 milliwatt power will be added to that budget. So 3.4 milliwatt and divider is another 1 milliwatt. So 4.4 milliwatt. So all this power is consumed. So that is the best strategy you should take.
So is the angle is 90 degree that is measured between the two?
Yeah, angle is 90 degree. I have the spectrum
and
data.
Phase noise, how much phase noise for one?
The phase noise, if you go through my work, 2016, the phase noise I received, I beat the world record. It is 134. So it is published in IEEE 488 in 2015. You read my paper there. Nobody has beat that phase noise performance.
Yeah, that is the requirement of the, this kind of requirement US defense having. So it is fulfilling the requirement.
Minus 224 form I got from this techniques. But that will not, later on in the Friday when I will go summarize, I will show the tricks, how to handle this phase noise like this. Okay.
Test setup have you shown you, right? Yeah. Oscillator buffer pad. Pad is given by ESD and you have a circuit. The buffer, we had any specification again, how?
I say 1 milliwatt power.
No, the buffer which is output of oscillator is connecting, right? So the
buffer is inside the chip.
Inside the chip. So the buffer, we had to be considered in layout as well as schematic itself. Schematic as well as layout.
I say that first you go for schematic level.
Then
again go for layout, then again do your post-layout simulations.
Okay.
If it is within 1% variation, accept it, don't, otherwise not. Again you retune your circuits.
Okay, buffer and...
First you design the schematic, get the simulation results, put the buffer, see the loading effect, say 10 picofarad, 100 picofarad, like that. You see whether the oscillation changes or not. You clear?
Yeah.
Because the buffering means key. Your input is isolated from the output loading. Now you simulate that you add in the load say 10 picofarad cap. Then what will happen? Your capacitance will now reduce, you will increase, that will pull down your frequency. So if you don't see the effects within 1%, then you are free. That means your buffering is done well, it is isolating.
The variation should be 1%?
Within 1%.
Within %. And next, after pad, there is bonding wire. It's a off chip or on chip?
Bonding wire, which is being, I showed the rectangular pad, and the pin that is out, you know, the chip, the ceramic chip is there, but in the package itself, the bond wire connects the pin and the pad. So you cannot see it, but if you open the black one, this IC, you can find those bond wires.
It's a packaging.
It's a packaging package. Inside the
Thanks.
So the loop, what is the length and how do you loop it? That tells you what will be your inductance of this. That is extremely important. And when two parallel such inductors, the loops are there, then the capacitance will be added. That will shift your frequency again. So don't use that parallel loops here and there. Minimum such bond wires, but you know, sometimes inductor takes a lot of power.
Is it to get the better phase noise? 3 dB better phase?
It is not that. Phase noise is, I already give you the tricks, KVCO. Don't get pursued by going to higher tuning range to increase your KVCO. KVCO is the damn thing. So try to make it within 20 to 30 megahertz volt. If you make it to 78 to 100, you can have a very good tuning, small change, but that is hell your things that it will make your phase noise performance worst. So there is the game. So KVCO by this band select one, and also I'm not showing you all the tricks here. I made some tricks to make the linearity of that. So the control voltage which is coming from my charge pump, that has to be somehow managed. Somehow we have to do something. Yeah.
I didn't get the reason of generating twice and then divide by 2.
Yeah. Because these are very standard questions of transceiver design. Why you require the both in phase and the quad phase components? Because you know that if you take the Fourier spectrum of any signals, you will get two sidebands, right? So one sideband is required and other sideband is not required for your extraction of your signals. So what you do that you take the signals and then you multiply with called is Hilbert transform. One is untransformed signals and another is the Hilbert transform signal which is multiplied by j omega, right? J. Now these two signals is fed to your LNA and finally fed to the mixer. So now this in phase and quad phase, what will happen? One of the sideband will be added and other sideband it will be subtracted. So actual energy is now conserved, and so that the sideband which is having the constructive superposition would have the highest energy. And this part which is not required, that is say omega LO minus omega RF, which is your requirement part, we have the amplitude. So that's why you require an in-phase and quad-phase components. So it is basically to extract the signals from one of the single sideband one. So if you look at the Hilbert transformations, it will be clear to you. Yeah.
Sir, in VCO core, LC negative resistance oscillator, we are using binary weighted switched capacitors. So along with capacitor, we are using transistor as well.
Along
Together.
this is as a switch.
Yeah.
This is a large signal. Mind it, this is not small signal.
Yes.
It's a large signal, just switch.
Yes. Can't we use the transistor itself as bank capacitor here? Because
No.
all are connected in parallel.
No. That MOS capacitor is very much temperature and process sensitive. But here the band select switch, you need a very robust capacitance. So that capacitor should be MIM cap. So I have used those as a metal insulator, metal capacitors, where the temperature and the process variation is much less. But that only I am using the transistor to switch it. That's all. So do not use the bank capacitors is a MOS cap. MOS cap its process variations, and you know that MOS cap will give you the capacitance value is not that big. But your MIM cap you can have much better capacitance.
Is it not sufficient capacitance value of the MOS transistor if we vary the metal which is used for the MOS transistor?
No, in a metal mumps, it is your design. Only the area of the metals are actually give you the capacitance. If you look at the MIM cap, these are two metal layers separated with the oxide layers, and then the area of the metal is giving you epsilon A by D.
Correct.
D is fixed by the process guide, which is 1 micron in your case. So you can think of what is the area, okay, effective area. So that area gives you the capacitance. There is no such design rule.
If I can vary SiO2,
there is absolutely no option to change SiO2 because it is a standard CMOS process. So you have no option to touch their process. If you have a touch, you can want to touch your process, then go to hafnium oxides, high K dielectric, but there is no options. It is a standard CMOS process, unfortunately. It is not your own design, it is from foundry.
yeah,
And the foundry is
instead of
from
full custom transistor taking, can I design my own layout?
Sure.
Just use it.
You can use your own layout because each wafer will cost you $100,000 US. And the wafer we are talking about that cost me 2.5 lakhs. So 4,000 US dollars. So 4,000 and 100,000. So bear the cost and enjoy life.
Okay, thank you.
Question? Yes, question?
Yes, sir.
Question. Yeah.
Sir, what is an effect of scaling, voltage scaling on the this phase noise performance of the oscillator? Is there any effect?
If you go for 180 nanometer and 65 nanometer, then lower feature size will offer better phase noise. Answer is very simple because the lower phase noise for 65 nanometer you can have better Q. Quality factor and phase noise is inversely proportional to 1 by Q square. So you will have better Q in, I say that in 180 nanometer process Q is 3 to 4, whereas the 65 nanometer you can go to 10, even 20, and 1 by Q square of that, so you will have a better phase noise performance. Clear? Answer should be crystal clear.
Yeah, hi, this is what I am going to, what is this in the picture, that is the schematic view, is the oscillator. Of course, this is the LC oscillator as already has been discussed, but this is designed for the 10 gigahertz for 65 nanometer TSMC process.
10 gigahertz oscillator.
Yeah, and the application is here is little different. The application is basically about a serializer, deserializer. Basically, serializer, deserializer is some kind of data communication network device where we have to take a bunch of parallel data and coming back and make it to the serial data and transmit to the optical fiber cable. So here, maybe the phase noise requirement is not that much stringent because we don't have any kind of adjacent channel interference which is available for the wireless communication. because it is all our guided media. But the fact is that this should run for 10 gigahertz one options, and another thing is that the power we are talking, but mostly the fact is that the frequency here. The frequency dependence is the problem, and as already you have came to know that the startup condition is basically GM into the RP should be greater than 1. The real fact, it would not work in the real design. The fact is because the GM is the what you are showing, where GM into RP just greater than 1, because this is the loop gain, and loop gain should be greater than 1 to have the startup of the oscillations or the sustainable. But the fact is that this scenario is much more worst what we are now writing here, because first of all we are not considering about our cross couple transistor pair output impedance, because we thought this is of course the giving of the impedance or resistance of -2 by GM, and we know this -2 by GM, this resistance has to be nullified to the actual parasitic parallel version of the resistance of the inductor. But the fact is that you have a current source which is shown here, this is the cross couple, this is one transistor pair, this is one transistor and this is another transistor. The both are cross coupled to generate the negative resistance. Of course, the negative resistance is generated by the biasing condition, it's not real thing, but this has to be, if I have to compensate only by this was okay, because I know that GM is again √2 ID something like this, though this formula is not actually valid for this very deep submicron technology, but still I see that if I increase my current, or if I have to have a particular GM, I have to have a particular bias. But the fact is that every cross couple pair having its output resistance, which is directly connected from the drain node to the source node. Okay? So what happened if you just imagine this, this both resistance will come into the series and act in the parallel. Basically, this RP will have a twice R0 will be in the parallel version. So you have to compensate RP parallel twice R0 with the GM. So your gain condition will be like that. Your gain condition will be like this. This -2 by GM should compensate with RP parallel twice R0. The fact is that in the 65 nanometer case, R0 is actually less, and so this value will be less, and GM you have to increase because to compensate. So it means that you have to burn more power, which is not actually visible from the normal way. So what I am saying that, so the current consumption here is around 8.5 milliampere, which is maybe theoretical, maybe 3 milliampere. So this is one problematic situation. Secondly, if you see this particular, okay, I will see from here. If you just see this cross couple pair, you can see this is the drain node. So drain node having the drain to bulk capacitance and as well as drain to gate overlap capacitance. So this drain to gate overlap and drain bulk capacitance will come into the picture again to your actual MOS varactor. So it means that your frequency operation will come down. So if you have to increase the frequency of operation, what you have to do? You have to reduce the inductance value. There is no other choice. So the TSMC, basically this process actually giving a very nice scripting, which will show you it is theoretically possible, but practically it is really impossible to find out a proper inductance value for your frequency of operation. So they will give some kind of script and you have to run that, so that, for example, here I am using around 0.2 nanohenry, that is 200 picohenry is the inductance value, and the quality factor is around 35, but only for that particular point of operations. Okay? So again the problem is again the twofold. If you see this RP is the parallel version of the resistance, and this is basically, as already spoken, that this is 1 plus Q square, correct? This Q is 35, and RS is generally for the 65 nanometer process for a top metal layer inductance, it's around 0.4 ohms. So if you multiply it with Q is equal to 35 and square, and approximately you will get that RP value will be around approximately 550 ohms. So approximately 0.5 kilo ohms. Okay? So the thing is here, the problem is here that you know GM, if I again consider the wrong assumption that GM RP should be greater than 1, let us say that means GM should be greater than 1 by RP, this RP again depend on the RS into 1 plus Q square. Okay? Approximately this is RS Q square. So what I should say that GM should be greater than 1 by RS Q square, and then it means that GM should be greater than RS omega, that is my frequency operation, and inductance, which express that GM should be greater than RS by omega 0 LS, this square. Okay? So it means that as you are going for a particular frequency operation, you have to have your Q factor also very much important. And then the problem is that Q is itself is dependent on the frequency. So it's a iterative process, it's not a standard normal process. So this way, and another point is that if you burn more current, you have to have a more aspect ratio of these two transistors. So it means that their gate capacitance also will to come into the picture, which is parallel to the inductance. So it means again your frequency will come down. So there are multiple dimensions, you cannot go anywhere. If you go there, it will be problematic for somewhere. So this is a typically the thing. And second is, okay, let us have, we don't have that much time, better I'll go for, I'll show you some simulation. So we are generally simulating, we are generally using the harmonic balance for our phase noise calculation, and harmonic balance itself is the algorithmic. It's a algorithm, and this is provided by the Spectra RF itself, but you have to have a separate license. It's costly. So anyway, that means that you have a, let us just okay. Okay. I'll just show you the phase noise performance. Let's say this is HV noise. If you are going for that, and you see the phase noise performance is here. So approximately at 10 megahertz, it is minus 100 TBC per hertz. And here is the corner frequency because it is a simulating problem. No, we are specified at 10 megahertz. Acha, 1 megahertz it will be around.
So in the design, phase noise is not so
Phase
important.
noise is not important.
We are actually using for IO.
Minus 85 dBc.
So this is for
86. No, I have also shown that minus 122, but this is not our case. This is our main purpose is for the jitter performance and our serializer purpose. It is not about our phase noise purpose, because we are not going for some wireless communication. Yeah, it is already published. Minus 122 is published.
that is published, measured, everything.
Yeah.
This is the new thing, 65. And that I have done in 130 nanometer. So that is for wireless communication, and this is for
This is not for wireless communication.
this is for 2.4.
This VCO will go for actually PLL. Basically, it will go for a frequency synthesizer to serialize the data. Is the important. Here is the not the important is our.
So this is just giving you an examples here.
This is swing around 1 volt. because my power supply is 1.2 volt, so 0.2 volt will be consumed by the bias transistor to make it saturation, and remaining thing is dropped across the, you can say, inductance and the RP.